Hello viewers, myself Dr. Mahantesh K, Associate Professor, Department of ECE, SJB Institute of Technology, Bangalore. Welcome you all to this online pre-recorded video sessions on electromagnetic waves, class 17, module 3, class 1. In this video, I'll be introducing you all to Poisson's and Laplace equations. The complete picture of this module will be studying the Poisson's and Laplace equations with its derivation and uniqueness theorem and some examples of the solution of Laplace equation to calculate capacitance, potential, and surface charge densities. And in the second half of this module, we'll be studying about steady magnetic field. Biot-Savart's law, where we will try to calculate the magnetic field at some point with respect to a steady magnetic field at some point with respect to a current carrying conductor, and Ampere's circuital law, which is almost similar to your Gauss law in electrostatic fields, curl, which is similar to divergence concepts in electrostatic field, Stokes' theorem, is similar to the divergence theorem in electrostatic fields, magnetic flux and flux density, electric flux and flux density, scalar and vector magnetic potentials. These are the reference book. The first one, Dr. McGraw-Hill from Hattenberg, 8th edition, is the prescribed textbook for studying this chapter. So far, we have calculated the electric field, flux, flux density, potential, and the other entities by knowing the electric field or by knowing the charge densities or the charge quantities. But most of the times in real time or in practical situations, the charge densities will not be known, but will be known in some regions. So hence, if we want to calculate the potential at some regions due to the charge distribution at some regions or knowing the charge distribution or the quantity of charges at some regions, so how are we going to calculate the potential? Most of the times we call these kind of problems as boundary valued problems. And the solution to obtain the potential is by applying Poisson's and Laplace equation. A useful approach to calculate the electric potential, which relates to the potential to the charge density, through the concept called divergence. So we have related the electric field with the charge density with the divergent relationship del dot E is equal to rho by epsilon naught, where E is electric field, divergence of electric field is equal to rho by epsilon naught. But due to the potential gradient relationship with the electric field, we know that E is equal to minus del V, that is gradient of potential. Therefore, the potential is related to the charge density by Poisson's equation and is given as del square V is equal to minus rho V by epsilon naught. But in a charge-free region of space, we know that rho V is equal to 0. That means we are trying to calculate the potential on the boundary by making the volume charge density as 0, which leads to the Laplace's equation del square V is equal to 0. Potential of a uniform sphere of charge density rho V is given by del square V is equal to dou square V by dou R square plus 1 over R square dou square V by dou theta square plus 1 over R square sine theta dou square V by dou phi square plus 2 dou V by dou R into R plus cot theta by R square dou V by dou theta is equal to minus rho by epsilon. Therefore, dou square V by dou R square plus 2 by R dou V by dou R is equal to minus rho by epsilon naught. Outside the sphere, dou square Y by dou R square plus 2 by R dou V by dou R is equal to 0. Therefore, V is equal to Q by 4 pi epsilon naught R, which is similar to your potential equation in electrostatic field. But inside, we can calculate V is equal to rho by 6 epsilon naught R square minus R square, which is equal to rho R square over 3 epsilon naught. So we can say that Poisson's and Laplace equations from the point form of Gauss law can be given by del dot D is equal to rho V, but we know the relationship between D and electric field is given by D is equal to epsilon E, and gradient relationship is given by E is equal to minus del V. Therefore, del dot D is equal to del dot epsilon E is equal to minus del dot del V is equal to rho V. Therefore, rho V is volume charge density. Therefore, del dot del V is equal to minus rho V by epsilon. So we can derive the Laplace equation from this Poisson's equation by making rho V is equal to 0. Therefore, del dot D is equal to rho V. Del dot del is equal to 0. So del dot del is a Laplacian operator, that is del square. Divergence of divergence is a scalar function and it's called a Laplacian function. So for a rectangular coordinate system, del square V is given by dou square V by dou x square plus dou square V by dou y square plus dou square V by dou z square. Whereas Laplacian for cylindrical coordinate system is given by 1 over r d by d rho, rho d by d rho v plus 1 over rho square by dou phi square plus dou square v by dou z square. Whereas Laplacian for spherical conductor is given by, or coordinate system is given by 1 over r square dou by dou r of r square dou v by dou r plus 1 over r square sine theta dou by dou theta sine theta of dou v by dou theta plus 1 over r square sine square theta of dou square v by dou phi square. To solve a given example, given potential is 4yz by x square plus 1. So it has been asked to calculate potential at rho v at P. Therefore, Laplacian in the given rectangular coordinate system, del square V is given by V is given by 4yz over x square plus 1. Therefore, Laplacian of R or V is given by 12. Therefore, rho V is equal to Laplacian of R dot epsilon naught. Rho V is equal to 1.062 into 10 power minus 10 coulombs per meter cube. And now we shall try to explain uniqueness theorem. If we know a volume charge density with a closed surface S, the function, the potential is given by V of x comma y comma z is completely determined on the surface. There is only one function V of x y z with given values on S. That is a boundary value that satisfies the Laplace equation. Example, a piece of metal has a fixed potential V is equal to 0 volts. Consider an empty hole in the piece of metal. On the boundary S of this hole, the value of V is the potential value of the metal. Satisfies the Laplace equation because of the theorem of uniqueness. So V equal to 0 describes also the potential inside the hole. That means the solution obtained are identical or unique. Thank you for watching this video. Hope you understood the concepts of Poisson's and Laplace equation and its application briefly.